This lesson is on the volume of prisms and cylinders. We'll start with volume in general. All volume is a unit cube. Just as we talked about, all area is a unit square. We now see that all volume is a unit cube. So we have a unit cube. It's 1 unit by 1 unit. So anything we're going to want to find the volume of, we'll try to put it into unit cubes. A convenient way, the most convenient way probably to do that, is to work around the rectangular prism, or a prism in general, particularly rectangular prism. With regard to the prism, we'll take it and slice it up into unit cubes, just like we did with the area, trying to go from a rectangle. Take a rectangle, slice it, count it. We'll do the same thing with cube. So everything's going to be relative to a unit cube. This is a unit cube. Okay. Here's a polyhedron. Here's a polyhedron. This one is 1 by 1, about 1 by 2 by 3. This is 1 high by 2 wide by 3 long. They are congruent. Congruent polyhedra have the same volume. Let's see, 1, 2, 3, 4, 5, 6. The volume of this one is 6 unit cubes. 1, 2, 3, 4, 5, 6. The volume of this one is 6 unit cubes. They are congruent polyhedra, and they do indeed have the same volume. Who would have thunk it? Okay, so if I have this polyhedron and this polyhedron, the volume of this one is 6 unit cubes. The volume of this one is 2 unit cubes. Oh, look. When I put them together, I get 8 unit cubes. Indeed, the sum of the parts is the whole. Here are postulates regarding the cubes. Remember, postulates are things, it's a synonym with axiom. Postulates are things that we accept without proof, although they might be proven in another circumstance. We will accept it without proof. A theorem will prove it, or will at least see that someone else has proven it. About volume, we're going to talk about how volume is done, how it's done for the purpose of these calculations. So let's start with a piece of green paper. Actually, it's green foam core board, but that's just as well. It has 2 dimensions in our mind anyway. Really it has 3, but we'll say length and width, and let's say it's 5 by 4, so that this is 20 square units of green. Let's say it has no thickness, although this one really does because it's real, but we're going to pretend it has nothing. So we'll pile it up. We'll take another one that's identical to it. We'll pile it up too. And another. Okay? The first one had no thickness. The next one had no thickness. The next one had no thickness. So now we have 3 no thicknesses, and this has no thickness. Well, let's pile up some more. There's some more. Now I got a whole bunch of them, none of which have any thickness, and together they still have no thickness. How interesting. Okay, well, how about a big pile of them? So here I've got a whole bunch of piles of green cards that are 5 by 4, 20 square units, but no thickness. 20 square units, no thickness. Okay, well, I'm not doing too good on getting volume since I have no thickness. So what if I pile in, stuff in 1,000,000 green cards in between each one of these? Would there be any thickness? No, because 1,000,000 times nothing is nothing. Between each one of those million, I put another 1,000,000, and 1,000,000, 1,000,000, 1,000,000, all between this space right here. 1,000,000 of them, and then 1,000,000 between those 1,000,000, and then 2 trillion between each one of those, and I keep doing it, and I keep doing it, and I keep doing it. more and more and more and more till it's infinite, more and more and more and more. Finally, there's thickness. It's like a mystery that you'll explore more when you get to calculus. But for right now, we can just observe that, oh my goodness, we did finally get some thickness. So let's say that this again is a 5x4 green piece with no thickness. I pile up a gazillion of them until finally, mysteriously, I have a thickness of 3 inches. So how much white foam corridor is there here? Well, there's 5 times 4 times 3 tall. 5 times 4 is this surface, also the bottom one, which we call the bases of the prisms. It's piled up 3 inches tall. So this is 5 times 4 times a depth of 3, are 60 cubic inches of foam core board. Notice what we get when we do it. Since they were all exactly the same size, there are now faces. 4 faces in this case, all of which are rectangles, that are formed because the pieces of green paper that were piled up just happened to be exactly the same size, so they ended at the same size, and so we have an infinite number of them. Then we have a face, a face, a face. So this is one way to look at how we could create a rectangular prism, and it's base times height, length times width, times the distance between the bases, the height. Length times width times height, which is usual formulation for a prism. Does it work if it's not square? It does. Looky here. Here I've got a bunch of circles. It's really, you know, cork coasters from Target, but we're going to pretend that it's a circle that has no thickness, even though it's got a lot of thickness. We'll just pretend. So this is a circle. Let's say that the area of this circle is approximately 10, just to be for an even number. So this is approximately 10. So I've got 10 left and right, 10 square units up and down, flat, no depth, no depth, no depth. I put 2 of them. I have twice no depth, which is no depth. Some more of them, no depth, no depth, no depth. A gazillion of them, still no depth. Even more of them. Okay, I take every one of those and I put 27 million in between each one of them. In between each one of those, I put 37 billion. And I keep doing it, and I keep doing it, and I keep piling them up between these two in this distance apart. And I keep doing it, and I keep till finally, there's infinite number of there, and mysteriously, I have thickness. A mystery which shall remain for a while at our current level of mathematical knowledge. So what do we have? We have a circle of approximate square area 10 square inches, and here a circle approximately 10 square inches, and between them there's 6 inches, all filled with this mysterious piled up nothing that's now mysteriously something. Okay, so 10 square inches in the circle, all piled up, 6 tall, so a total of 60 cubic inches of cork. The reason I'm saying them this way is because that's philosophical background for the formulas that we're about to use, and you can do it with any shape. It works for any shape. That's with a rectangle and with a circle, but here you can also do it with a pink triangle. If you take a pink triangle that has length and width divided by 2, but no depth, you can't see it, it has no depth, you pile them up, you pile up some more of them, and then you pile up some more of them, and then you pile up like a whole lot of them so that you have a really big pile here. It does the same thing. It creates flat sides, which are faces, because they were all the same size that you piled up. Another flat side that makes a rectangle, makes a rectangle, makes a rectangle. This is one way of looking at how you can build a triangular prism. So That's one way to look at it. It works the same no matter what the shape is. You pile it up, it's going to work. So specifically for prisms and cylinders, that's kind of how we have our background for how to do the formula. So the volume of a prism is volume equals the area of the base times the height. Recall that capital letters tend to equal things that were calculated, and lowercase letters tend to equal things to represent things that were measured. This is the area of the base, the yellow, times the height. If it happens to be a rectangular prism, that's our length times width and then times height. Length times width for the area of the base times height to give the volume of the prism. Same deal on the cylinder. Notice that we use exactly the same formula, but truth be told, not many people are going to use this form of the cylinder formula. This one's the one they're going to use, because if it's a cylinder, the base is always round, and round is pi r squared. So most everybody just says pi r squared h, but be aware that they were formed in the same fashion, and philosophically you can think of them in the same way, as taking the shape, piling it up, creating straight sides that are either a curved plane in a cylinder or a rectangle in a prism. So we can kind of play with these a little bit and see what difference we make and what difference we don't make. So here's my rectangular prism formed of green cards. I'm going to make it crooked. Oops. There we go. So what did I do? I made it oblique. Remember, a right pyramid is one that the line that passes through the center of the two bases is perpendicular to the base. This is not one of those. So here we'd have the line passing through the center of the bases. Notice that it is not perpendicular. Center of the base up there, if I had it in the middle of it. Center of the base down there, if I actually had it in the middle, would be right along in here. So this is oblique. It is not right. So there's one way of being oblique. You can also have other ways of being oblique. And you can do them both at the same time. And that works just fine. Now what I'm looking at here is volume. So here I had length times width times height, and that gave me the volume. If I do it this way, okay, look carefully. Look carefully. Here's my rectangular prism. That's right. I'm going to make it oblique. Watch carefully. Watch carefully. There we go. Oh, look. Oh, look. It's not right anymore. But please observe that no foam core and no green cardboard was harmed, was created or destroyed in the making of this oblique prism. The same volume is still here. It's just rearranged. I shifted it around. The same volume is still here. So it really doesn't matter if it's oblique or not, or even if it's crooked a couple of times. I can bring it back like this. That's just fine too. Still the area of the base, length times width, times the distance between the bases, height, is the volume of it. Nothing was created or destroyed. Same deal for the cylinders. There's a certain amount of cork here. I make it oblique. It's still the same height. The height is still the same. See, here's the height when it's right. Here's the height when it's not right, when it's oblique. The height is the same. The surface area, the area of the base is the same. The area of the base times the height is the volume, and it remains the same. So what we see is that no matter how you configure it, you can make it oblique or it can be a different shape. if the area of the base is the same, and it's made piled up with straight sides, that the volume will be the same, and the cross-sectional area wherever will be the same. This is Cavaliere's principle. Solids with the same height and cross-section area at all levels have the same volume. So you know that if they're the same, it's going to work, and that also means you can pick any place you want to be what's going to be the area of your base. So obviously, usually we pick the top one or the bottom one to call the base, but since it's the same all the way along, it was formed by piling up the same thing an infinite number of times, then I could pick this one right here. And that'll work just fine. It's the same. It doesn't matter where along this cylinder or where a prism I choose to take the measurement of the cross-section. We'll still get the same thing. So even if you've got something like really weird, let's look at really weird. So you've got say you have a shape that's a flower. That's flower girl. And you've got like an amoeba. There's amoeba boy, amoeba dog. I don't know what that looks like. Amoeba. And then you've got, oh, I don't know, square guy. So each of those have the same area. That each of them have the same area. If you make little shapes just like that and pile them up like we just did with the other, and you'll come up and they'll make a pile, and it'll look something like this. You'll have this little straight-sided thing that's a three-dimensional solid of flower girl, and then you'll have amoeba boy or amoeba dog or whatever he is here, and we'll make the other base being the same thing. Doesn't matter what the shape is, they have the same. What's going to happen then is it'll be the same volume. Area of this base of square guy, you pile them all up. If the surface area, if it's the area, a flower girl and amoeba dog and square guy, if these three are congruent, the area, and it's formed in the same fashion so that the upper and the lower base are the same, everything along the way is like piling up amoeba dogs all the way up, that it's not going to matter where you choose to take a cross section. The area will be the same, and since the area of the base is the same and they're piled high the same distance, it's the same distance between the upper and lower base, then the volume of these three figures is always the same. A few examples about this, how it might work out. Okay, this one's probably the easiest. So I've got an irregular figure. I'm looking at it. I'm looking for two that are parallel and congruent. Those are going to be the bases. Those are going to be the things that are piled up in my loose terminology. That would be the front and the back. Notice the front and the back are going to be the same. So we find the area of the front and the back, and then pile them up for 4 inches, being the height. We'll be able to find the volume of this. So the area of the front. Well, I can either think of it as 5 units by 4 units, which is 20, take off the corners 2 for 18 units, or I could divide it up and say maybe 5 by 3, 15 on the lower portion here, and then 1 by 3 on the top, so 15 plus 3 is 18. Either way, I'm going to get that the area of this face, of the base, is 18 units. I multiply it by 4 because that's how far it is between the bases. The distance between the bases, or how much we pile up, is 4 units. That would be 18 units times 4, which I think is 72 cubic units for this shape. You're just going to divide them up and see how it goes. Some others here. This looks like an upside down T for the bases with a distance between them of 2. Here, laying down L or long leg L. Figure the area of the front and the back with a distance 1 in between. You'll have other simple ones to do. Here is a triangular prism. Here's a cylinder, several of the others. Again, no matter what the shape of the base, you find the base and multiply it by the distance between the two bases. And here endeth the lesson.